Hi, this is Paul Proyas with Metaphase Lighting Technologies, and this is an application note on choosing the right machine vision light. Here's what I'm going to be covering, going over some lighting considerations for choosing the right machine vision light, and then we're going to go through all these different lighting techniques and to show why you may use one of them in an application. Okay, so choosing the right machine vision light, there's many different ways to go about this, many different checklists, and this is an iterative process, so you can do these steps in order, but you're often going to go back and forth and do a lot of experimenting, checking the sample, the camera, your mechanical setup, and seeing what results in that best image, that best signal to noise ratio, and what gets you the information needed to make the inspection decisions for pass or fail that you need. That's the goal. So first, area scan versus line scan considerations. We have another application note going into more when to consider line scan, but overall it's based on the size of the object, the complexity, shadowing, and what the complexity and the budget is for the project. With line scan, one thing, if the camera or the object is moving, that may be a hint that you might want to look at line scan as a consideration because you often need that movement to do a line scan application. Determine the wavelength of the light required, maybe visible, or maybe you're looking at fluorescing images where UV is needed, or maybe you need kind of like what we call a poor man's X-ray, and maybe some SWIR applications might work for you. But looking at what the possibilities are and what your options are in the environment you're working at. You can't use every type of wavelength in every application depending on what the safety considerations are, the personnel. Other things to think about are, do you need different wavelengths at different times? Instead of multiple lights, you may be able to go with a multispectral light where you can turn on different wavelengths using normally a 0 to 10 volt dimming line. Or do you need a very broadband electromagnetic spectrum, which we'd call hyperspectral, where you get a lot of different wavelengths all at once at the same time? Determining the intensity required, what gets you the best picture? And if you don't have enough intensity, do you need a brighter light or can you strobe that light? Consider the lighting configuration based on the size and shape of the object, your field of view, the camera resolution, and the reflectivity of the object and the background. So this is where you're going into, or you can use front lighting or back lighting, or do you need dome lighting? Do you need diffused axial lighting? All the different configurations available to us in the machine vision world. Consider the cost of the light versus the camera. Okay, so if you're using a cheap camera, you might want to match that. If you're using something very expensive, like the SWIR lighting camera, you may want to make sure your illumination matches that. It doesn't make sense to have a mismatch there. And often a small increase in the cost of the light can make a world of difference and can maybe even bring down the cost of the camera that you're using. And then challenge the lighting solution. Is this really the best one? Are we just doing it because we've always done it this way? Is there something better to get better contrast or to make the process more repeatable, easier to use? Just don't settle with what you've always gone with. Take a look at these considerations and see if you're giving your customer the best choice. All right, so multispectral, as we discussed before, it's individually controllable RGB and IR LEDs to maximize the contrast. So you put normally one wavelength on at a time. You may be inspecting something for flaws, and then you switch to UV to see if there's a barcode there. Just one example, or sometimes different defects show under different lights. You may want to do a green and then go to a red. But it's just really one wavelength at a time, but you have multiple wavelengths within that light. Works great when it's paired with quad linear cameras, and we often see it in print inspection, banknote inspection, and packaging and label inspection use cases. Here's an example of a couple of hyperspectral LEDs. The top one is visible NIR and SWIR broadband wavelengths going from about 1,000 nanometers to 1,600 nanometers. And then below we have a visible NIR going from about 360 right into the UV wavelengths up to about 960, kind of the end of the IR spectrum there. So with this, you can match the lighting wavelength that's being produced to optimize what your camera can pick up for its range of wavelengths. So darkfield lighting is lighting an object with oblique or grazing light. If you take a look at the top right photo here, you can see the light's at a high angle and it's hitting the object and then bouncing off and not going directly into the camera. Whereas on the bottom there, you see that machine vision W where the light is co-located with the camera, shining right down on the object, and those rays would bounce directly into the camera. So when you use this dark field, very oblique angle type lighting, you can get reduced surface glare, get enhanced contrast, and you can highlight specific surface features that may not be visible when you're using just bright field illumination. Here's a bright field versus dark field example. So you see on the left image there, we're using traditional lighting co-located with the camera shining down, and you get this kind of blurred image, a lot of reflectivity, can't quite make out. And if you change the lighting angle to dark field, you can see exactly what we were looking for. And so it's an easy way. You're not really changing anything but the angle of light in your mechanical setup to get a whole different image. Collimation, sometimes known as telecentric, is the process of making light waves parallel to each other by passing them through some type of collimator lens. So you can get improved accuracy and precision, so you can reduce distortion, and you can increase your depth of field. For line scan, it allows you to go to much larger working distances, where a lot of times with line scan you have to be only 75 millimeters away, 100 millimeters away. You can actually stretch your distance out. And you can see collimation example here on the left side where we're looking at screws and the threads in them. It just gets you a lot cleaner edges where you can actually do some measurement and gauging, where if on the right side without that collimation, it's blurry, you really couldn't get an accurate measurement from that. Polarization is the process of filtering light waves in a specific plane or direction. It often leads to reduction in glare. So you can increase contrast and detail, improve accuracy and reliability, and you can enhance color detection. So you can see the bottom image did not use any polarization on there. Very dark, couldn't see the label, but then when you add polarization here, you can see we pick up the color in there and we get a lot less reflection from the plastic. Dome lighting illuminates an object from all different directions. You can see all the LEDs are actually in the base of the dome and they reflect up to the dome and then back down on the object. So this results in very uniform illumination. It reduces shadows and reflections, enhances your contrast and detail, and you can get increased depth perception. Here's a dome lighting example that was able to reduce false rejects from 5% to 0%. So you see standard lighting here on the left, you see a lot of reflection, can't really get a lot of contrast or detail to see if things are there, missing, lined up. Whereas on the right side, when we do dome lighting, a lot more uniform lighting, a lot less glare, and you can see a lot more detail in the object. So here's another example of dome lighting, where on the left side we had a very reflective packaging where we couldn't even make out the expiration date. Then on the right side, we put it under a dome light, and then you can see it comes out very clearly. Okay, I know you can't ask me any questions here, but you can always go to metaphase-tech.com to learn more, or please email us at sales@metaphase-tech.com, and we're happy to help you out with your applications. We have an application lab where we can take samples. We have an evaluation light program where we can send you out lighting to test, and we really want to be your technical consultants and help you find the right machine vision solution. Thanks for listening.